Hi, this is Geometry, Circles, Chords, and Arcs. Our objective is to use congruent chords, arcs, and central angles, and to use perpendicular bisectors to chords. In this diagram, segment LM is a chord because it has endpoints on each side of the circle, but it doesn't go through the center point P, so it's not a diameter. And LM is an arc of the circle. The length of a chord, which is a segment whose endpoints are on the circle, is shown here in this diagram. PQ is the chord, and it's a segment whose endpoints are on the circle. The diagram shows chord PQ and its related arc PQ. It's essential that you understand you can use information about congruent parts of a circle or congruent circles to find information about other parts of the circle. The following theorems and their converses, you remember converse is when it's reversed. The if becomes the then becomes the if. The following theorems and their converses confirm that if you know that chords, arcs, or central angles in a circle are congruent, then you know the other parts, two parts, are congruent. So it's quite a bit of notes when it comes to the theorems here, this evening's notes, but they're very simple when it comes to the application of them. So Theorem 12.4 and its converse. The theorem is within a circle or in congruent circles, congruent central angles have congruent arcs. So in this picture here, angle AOB, so that's this central angle here, AOB, is congruent to this central angle COD, and therefore the arcs are congruent. Arc AB is congruent to arc CD. And then the converse of that, if the arcs are congruent, then that means the central angles are congruent. So pause the notes as we go along if you need to write things down. I'm going too fast, but there are quite a few theorems tonight. Theorem 12.5 and its converse. Within a circle or in congruent circles, congruent central angles have congruent chords. So again, we're going to talk about that angle AOB and this angle COD. So it's the same two angles we just talked about in the last picture. That means that this chord that is formed by segment AB is congruent to this chord, segment CD. Because the angles were congruent, then the chords are congruent. And the converse is, if the chords are congruent, then that means the angles are congruent. Theorem 12.6 and its converse. Within a circle or in congruent circles, congruent chords have congruent arcs. So in this picture here, segment AB is congruent to segment CD, and therefore the arcs are congruent. Arc AB is congruent to arc CD. So if the chords are congruent, then the arcs are congruent. If the arcs are congruent, then the chords are congruent. So it doesn't matter which one you know that if the chords are congruent, then that means that the arcs are congruent. And you also know that if the arcs are congruent, then that means that the chords are congruent. Okay? Theorem 12.7 and its converse. Within a circle or in congruent circles, chords equidistant from the center or centers are congruent. So in this case, OE, that's this segment, is congruent to OF. They're congruent. So because they are congruent, then the chords that they are both perpendicular to are congruent to each other. And then the converse would be true. If segment AB is congruent to segment CD, if the chords are congruent, then that means these segments here would be congruent. OE would be equal to OF. So finding the length of a chord. What is the length of RS in circle O? RS is this chord here. So because OQ is 9 and this segment is 9 and they're both perpendicular, then you know that RS is congruent to RP. Well, if this half is 12.5, then that means that this half is 12.5. So the whole thing, R to P, is 25. So RS would be congruent to it. RS would equal 25. What is the value of X in example B? And again, the chords are congruent. 18 and 18 is equal to 36, and because these segments that went from the center of the circle out to the chord are perpendicular, that means that they are congruent to each other. So if this piece is 16, then X is equal to 16. So remember in class when I was saying there's just some rules to remember about circles. These are just some rules you have to remember about circles. To write them all down, we'll do some graphic organizers too. Here's some more. Theorem 12.8. In a circle, if a diameter, so remember a diameter is a segment that goes from one side through the center point to the other side. If a diameter is perpendicular to a chord, so in this case CD is the chord and AB is the diameter that's perpendicular to the chord, then it bisects the chord and its arc. So because AB was perpendicular to CD, it bisected CD, bisect means to cut it into two congruent segments, and it bisected the arc. So CA, arc CA, is congruent to arc AD. So because this was a diameter and it was perpendicular, then we know CE is congruent to ED and arc CA is congruent to arc AD. Theorem 12.9. In a circle, if a diameter bisects a chord, so now we're saying if the diameter cuts the chord into two congruent segments, then you know it's perpendicular. And if you know it's perpendicular, then you could go on to prove that CA is congruent to AD. And in a circle, the perpendicular bisector of a chord contains the center of the circle. So if AB, that's this segment, is the perpendicular bisector, then you know that AB is a diameter. It contains the center of the circle, and that's the definition of a diameter. What is the value of the variable to the nearest tenth in this picture? Well, because Kn is perpendicular to this chord LM, then we know that it bisects it. It cuts it in half. So if all of LM is 14, then that means each piece is 7. It's perpendicular, so it forms a right angle. You don't know R, which is the hypotenuse of that right triangle. So using the Pythagorean theorem, you could solve for the length of segment LK, which is a radius of this circle. And all radii are congruent, so if you needed to, you could say that you know the radius of, that all of the radii are congruent. So we would say 3 squared plus 7 squared is equal to the radius squared. So 9 plus 7 times 7 is 49 is equal to the radius squared. So 9 and 49 is going to give you 58 is equal to the radius squared. The opposite of squared is square root. So the square root of 58 is your radius. The square root of 58 is approximately, remember we want to round to the nearest tenth. So because we're going to get 7.61, it's approximately 7.6, and it was centimeters. So we use the Pythagorean theorem in order to solve for the radius of this circle. And from here we can now find the area because we know the radius. We can find the circumference. What is the value of the variable to the nearest tenth? So like I was just saying a second ago, all radius of a circle are congruent. Radius, by definition, are from the center to the side. So BE is a radius. Well, we want to find the value of y. This line here, BA, is also a radius. So it is 15. This is the perpendicular bisector because it was 11 and 11. So now we can use the Pythagorean theorem to find the value of y. We're going to round to the nearest tenth. So we know that y squared is leg plus this leg is 11. 11 squared is equal to 15 squared. So y squared plus 121 is equal to 225. So y squared is equal to, we want to say 225. We want to subtract 121 to get 104. And then to undo squared, we're going to do square root. So we're going to get that y is approximately, we're going to round to the nearest tenth again. When you do the square root of 104, you're going to get 10.19. So it's approximately 10 point, because it was 19, it's going to be 2. And we don't have a labeled unit here, so we're just going to call it units. That's going to conclude tonight's notes. If you didn't pause the video while the theorems were up, you may want to go back and do that. You're going to need to really study and memorize these rules of circles.